Okay, so obviously here we're looking at the relationship between how long an animal lives in years and how long it stays in the womb on average in days. The hardest part of this is probably entering all the data into the calculator, all 40 animals. And since for this activity we want to use longevity as the predictor, and we usually have the predictor in L1, I have those values in L1. Although you could do the regression making any list that you want the X list. So technically it doesn't matter. The first thing that we did after we entered the data in was we found the mean gestation period, and I'll explain why that matters later. You know how to find means now. 1var stats, and our gestations are in L2, or my gestations are in L2. That's the mean, 194.325 days. And please know that if you put a bar over a word or a letter, it signifies that it is the mean of that variable. So on average, these 40 animals stay in the womb 194 days about. The next thing is to find the regression equation, meaning the least squares regression line. This can be done very easily with the calculator. Stat Calc 4 or Stat Calc 8. I'll choose number 4. My X variable is in L1. My Y variable is in L2. No frequency list. And I can store the regression equation somewhere, but I'm not going to. Calculate. There you go. No need to draw a line on a scatter plot and guess what it is. We have with certainty the line that minimizes the sum of the squared residuals. That's what it is. The first coefficient is the slope, and the second coefficient is the y-intercept. I and also the College Board want you to be able to replace x and y with what they stand for. It's pretty easy. You just look at what the x variable is and what the y variable is. My y variable is gestation. That's the dependent variable here. Please put a caret symbol over it that indicates that you are predicting or estimating gestation as opposed to knowing gestation with certainty. That's the slope from the calculator. That's the x variable. And that's the y-intercept. Okay. Any questions so far? All right. Secondly, we want to interpret the slope and the y-intercept. This is also an essential skill as per the College Board. If you know that slope is rate of change, I think you can handle it. So you can think of 13.126 as being 13.126 to 1. You need to identify the units. Well, slope is change in y over change in x. So the units are going to be the units for y over the units for x. So what are my units for the y variable? Kilograms, pounds. Hello, what's that? What are the units of gestation? Days. And what are the units of my x variable? Years. That will help you in interpreting the slope. 13.126 days for every 1 year. Okay. So the slope signifies that for each additional year an animal lives, the model predicts they will stay in the womb an extra 13.126 days. And technically that's an average. Okay, any questions on how to interpret a slope of a regression line. Okay, and you'll get more practice through the homework. Then we need to interpret the y-intercept. 21.713. Kilograms, pounds, coulombs. What is it? Yes. Days. It's the same units as the y variable, and our y variable here is gestation. So, you know y-intercepts. They're the y value when x equals 0. In this case, longevity. So I'll say the y-intercept signifies the starting point for gestation, i.e., we expect all animals to have a gestation period of at least 21.713 days. Okay. And also you could insert the mathematical definition. It is technically the predicted gestation for an animal that has 0 years longevity. It never lives. Okay. Any questions on the interpretation of the y-intercept? Okay. Next question. Find the correlation. Easy. No need to find the z-score products and add them up and divide by n-1. The calculator has that all programmed in the background for us and does that all. So here's the Pearson product moment correlation coefficient. R, 0.663. What I can infer from this is that there's a positive relationship between gestation and longevity. So as animals get older or live longer, they have longer gestation periods on average, which makes sense. And but it's not a strong correlation, which implies that there are other factors that go into gestation, or that it's not a linear relationship. And it's always a good idea to look at your scatter plot to make sure that it's appropriate to report this coefficient, because this is only appropriate for linear relationships. Okay. And then the correlation squared, also from the LinReg screen, 0.44. We'll talk later or soon about what that means. Okay, by now, hopefully you know how to make a scatter plot. Maybe you don't know how to put the equation on the scatter plot, but it's not too difficult. So, second y equals number 1. Turn it on. Just choose the first type. X list is L1, Y list is L2. Make the mark whatever you want. And then you zoom 9. Okay, so as you can see, we have a positive trend. A very evident outlier here. And it's hard to be certain about linearity because there's so much scatter. But a general positive relationship is evident there. Now, to put the regression equation on, there's two ways that you can do this. One way is the manual way. I'll show you that first. So if you want to plot lines or any other function, mathematical function, you go to y equals. And then you have your equation that you found in number 3, 13.126 x plus 21.713. And then graph. Okay, that's the line that minimizes the sum of the squared residuals. That's the linear model. And you can use that to make predictions for animals that aren't on this scatter plot, for example. Another way to do it that's more automatic, so let me just turn or delete that for a second just so you can see this in action. Every time you do stat calc 4 or stat calc 8, it gives you this option to store the regression equation. And you can store that in y1. Does anyone know how to access y1? I'd be really impressed if you do. It's kind of esoteric TI-84 knowledge. Very good. I'm impressed. vars stands for variables, yvars, and function, number 1. That's how you access y1. I would have loved TI to have made that the default. Oh well. And then when you calculate, what you'll notice is when you go into y1 or y equals, it's there for you with all the decimals available. But usually we don't need that level of precision. And then graph, and then it will be on there. Okay? All right. Number 5. Put the predicted gestation periods in L3. These are the gestation hats. Models make predictions. What's the weather going to be? What's the stock price going to be? Etc. Okay, the calculator can do all these for us very quickly. So go into your stat editor. Go to the very top of L3 such that the heading is highlighted. And you are going to enter in your model because that gives you the predicted gestations. You could use, if you want to be ultra precise about it, you could go into vars, number 5, statistics, EQ, which stands for equation, and number 1, regression equation. And it will give it to you with all the decimals available. And then you have to replace x with L1 because that's your independent variable. So highlighting the x, you would then have to press second number 1. But we really don't need that amount of precision. So it would be fine for our purposes here if you simply typed 13.126 times L1 plus 21.713. Okay. And then hit enter. So with that less precise version, you still should be getting numbers that are very similar to mine. So the first predicted gestation is 284.24 days, which as you can see is quite an error because the actual gestation period for the baboon is 187 days. So almost 100 days off. Okay. Any questions on number 6? The symbol used for the values generally is y hat. In this example, it's gestation hat. Now, let's find the residuals. Hopefully you know by now that residuals are y minus y hat. Actual minus predicted. Okay, so go to the very top of L4, and you tell me what should I type. Savag. List 2 minus list 3. Actual y's are in L2. Predicted y's are in L3. Very good. And then enter. These are your residuals or your errors. As you can see, for the baboon, we were 97.24 days in error. The fact that it's negative means that the predicted value was higher than the actual value. In other words, we overestimated the baboon's gestation, as you can see clearly here, versus that. Okay? And then if you want, you can browse the list. Like, this is a pretty big error here, 226.77. That's for the camel. We didn't do a good job there. This one's pretty big, 272.02, 10, 425. The giraffe. Okay. Next thing I asked you to do, and I saw Ethan get, which was fantastic, plot the residuals versus the longevities. Well, your residuals are in L4. Your longevities are in L1. So this is pretty simple. All you got to do is go to your stat plot, second y equals, go into number 1, and change the y list to L4. That's it. Just one change. And then zoom 9. That's the residuals plot. The regression line no longer makes sense. So I'm just going to go into y equals and disable it by toggling the equal sign here, pressing enter over it. If you have it on there, it's not that big of a deal. Just ignore it. Residuals on the y, longevities on the x. So in my experience, if you are serious about making models, you are going to be looking at the residuals deeply. You're going to be analyzing not just how large they are, but also change over some variable. And that's what we're looking at here. How are the errors behaving over the longevity, over the x variable's values? The x-axis is a 0 residual, meaning that we had a perfect prediction. Very few animals are even near that. Okay. Here you can see this outlier here. Although it's definitely an outlier, it does not have the largest error. And what animal is that? The elephant. Okay. So we should definitely be concerned about this point, but notice that it does not have the largest residual. This animal here has the largest residual, and it's positive, which means that we underestimated its gestation period by a lot. Okay, meaning that the line was below it. And you can hit trace and see these values if you keep pressing to the right. And maybe I can get to that animal fairly quickly that has that largest absolute value residual. There it is. And we saw that animal before. What animal was it? The giraffe. Very good. Another thing to point out with the residuals plot is how much spread there exists in the errors over your x variable or some other variable. Do you have consistent spread here? You do not. And that can be an issue with modeling. Let's see if I can actually get this word. If you want to sound really smart, you can learn this word. It's like the equivalent of kurtosis. Homoscedasticity. This means equal variance. And then the opposite of that would be hetero. So this residuals plot shows heteroscedasticity. Okay. We have a lot less variance in the errors for animals that are in the beginning, animals that don't live a long time. And then the errors blow up, so to speak, as we get to the mid-range animals in terms of longevity. Okay, and then it kind of like quiets down again after that. You'll see later how heteroscedastic plots can cause issues, but at this stage, be aware of it. You can also tell, like, overall, are you tending to under or overestimate? Well, as you can see, we have a mixture here, but if you look at these mid-range values, we have a lot of kind of extreme positive errors, which are underestimates, and we don't have that equivalent thing going on the other side here. Okay? So the residuals plot is used to help you understand the model better and to understand if the model is appropriate. If you see patterns in the plot, that's generally not a good thing. That usually means that the model that you chose is not the most accurate one. Okay? Good. Any questions on the residuals plot? Okay. Next, put the deviations of the actual gestation periods from the actual gestation periods from the mean gestation period in L5. So this is going to be gestation minus gestation bar. Or y minus y bar. So let's do that now. Stat editor. Please tell me what to type. Matt?
Is it L2 minus 194.325?
Excellent. L2 minus 194.325. Okay. These are the deviations from the mean. This is what statistics is all about, studying variation. Not all animals have the same gestation period. So the baboon has a negative deviation. That means that it is below, means that the mean is bigger. So it's below average gestation. Okay? So these help us to understand variability. Next, put the predicted deviations of the gestation periods from the mean gestation period in L6. So symbolically, this is gestation hat minus gestation bar. Or more generally, y hat minus y bar. Okay? You're doing great. Tell me what to type. List 3, very good, minus list 5, also very good. And then enter. So the baboon is 7 days below average gestation. However, we actually predict that it should have been 292 days above average if we did this right. And we'll just double check. Our predicted gestations are in L3. Okay. Our mean gestation is not in L5. Okay. I recommend you go with your gut. My gut was not telling me that these numbers were correct. So that's what made me check. So let's try this again. L3, go ahead. Minus 194.325. Okay. That looks more reasonable. So we predict that the baboon would have been about 90 days above average in gestation. Okay? So these are the predicted deviations, these are the actual deviations. All right. On the back. Here's a scatter plot of the data. I did it in Excel. Scatter plots are very easy to do in Excel, and for your tracking project, you will do that. Or use a similar program. So let's label some things on here. What's this horizontal dashed line? And you can just say these out loud. Mean gestation. Very good. And the vertical line? Very good. Now let's look at these braces. Tell me symbolically the distance between the point and the mean line. What is it symbolically? The point and the mean line. How do you express that difference? We're not doing the regression yet. This is the mean line. Yeah.
The deviation.
Okay, can you tell me symbolically?
The amount of days.
So when I say symbolically, I want mathematical symbols.
That would be y minus y bar.
Nice. Okay, next one. The difference between the point and the regression line. Yeah.
Y minus y.
Very good. Y minus y hat. Or gestation minus gestation hat. Last one. The difference between the point on the regression line and the mean.
Y hat minus y bar.
Y hat minus y bar. Awesome. So understand the symbols used. Next, using the calculator, find these sums. Easy. StatCalc 1 gives me sums. It also gives me sums of squares, which is even better. So tell me, what list are your y minus y bars in? I disagree. List 5, right? So go to StatCalc 1, do it on L5. Interesting. The sum is 0. That's supposed to be, deviations from the mean should always add up to 0. This is what I'm interested in. This big number. 801,842.775. It's a measure of variability from the mean. Next, StatCalc 1. Where are our predicted deviations from the mean? Nice. I am so impressed today. Notice that the average and the sum are virtually 0. I don't think that's a coincidence. This is what I'm interested in. 352,720.106. That's a measure of predicted variability using the line. And the last one, what list? L4. Nice. Okay, these are our residuals. Yeah, this is some high-level stuff you're doing, so if you're getting this, give yourself a pat on the back. If you're not, that's okay too. I'm here to help you. 449,122.669. This is a measure of overall error. Now let's find these ratios. Y hat minus Y bar, that's 352,720.106. Y minus Y bar, that's 801,842.775. Let's do that calculation. It's about 0.44. Oh, and I apologize, I didn't answer this question. What are the common acronyms for these? This first one is sum of squares total. This one is sum of squares regression. And the last one is sum of squares error, because it's the residuals. All right, and then the second ratio here, y minus y hat, that's 449,122.669 over 801,842.775. Thank goodness we have calculators, man. .56. Okay, take a look at the front side. Where do you see 0.44? Squared, very good. And this one here is, what do you think? It's related to r squared. It's okay. It's might not be something you see right away. It's 1 minus r squared. Okay? So you may be wondering, what does this all mean? That's totally natural to wonder that. This numerator here, if you look at the expression, this is the predicted value minus the mean value. So this difference is the predicted deviation from the mean. And because those tend to add up to 0, we use a squared value. So this is the predicted variance. I know it's technically not variance as per the conventional statistical definition, but it will suit our purpose in terms of understanding what this fraction means. This here, this is the actual deviation from the mean, so you can think of the denominator as the actual variance. So this ratio is the fraction of the total variance, or the actual variance, that we are predicting using this model. And notice that's the same thing as r squared. You don't have to do all of this mathematics. What's really cool and can be shown algebraically is that the correlation coefficient squared is equivalent to the fraction of the variance in the y variable that is being predicted or explained or accounted for by the model, in this case the least squares regression line. Over here, this is an error or a residual. So this is a measure of overall error. The denominator is still the same. This is the total variance. So it's the fraction of the total variance that's made up of errors. We want the numerator to be as small as possible. If it was the smallest possible number, it would be 0, and therefore this would be 0, meaning that none of the total variance is made up of errors, and that would be the ideal situation. So this is the fraction of the total variance that's not being explained by the model because it's made up of errors. So just to summarize, r squared is the fraction of variance in the y variable that is explained or predicted by the least squares regression line using whatever predictor variable you're using, in this case longevity. 1 minus r squared is the fraction of variance not explained by the LSRL. In other words, the fraction of variance that's made up of errors. So for this data, 0.44 is the same as 44%. So as you can see, we have some deviation from the y bar. That's natural, and that goes into the total variance. And when we're using the model, we're predicting different variation. So we take the ratio of the predicted variation, which comes from the line, and make that a ratio with the denominator of the actual variation, then you get r squared. So 44% of the variation in gestation period is being explained by the least squares regression line. And that statistic is used to get an understanding of how good the model is at making predictions. 44% doesn't seem very good. And what that means is that the remainder, which is 56%, is not being explained. So we have the majority of the natural variance in gestations, the natural differences that we see, that's not being accounted for in a linear sense by this model. Other questions here, what values are always on the least squares regression line? Hopefully you can see that. Right there. The means are always on the least squares regression line. The root mean square error, what that is the sum, the square root of the sum of the squared errors over n minus 2. And we have the numerator. We calculated it before. It's 449,122.669. And we'll divide that by n minus 2. N is 40. There's 40 animals. So the square root of 449,122.669 divided by 38 is 108.7. This is in days because that's our y variable. And this is a measure of overall error when we're using this model to make predictions. So on average, we're off by about 109 days when we're predicting how long an animal stays in the womb, given how long it tends to live.